really varied world of particle accelerators. So those of you working in medical physics will be very aware of one very specific type of particle accelerator, but I work on many other kinds as well. So I want to introduce you to different types of accelerators and how they work, and different applications of those machines to give you an idea of what's out there. So to introduce myself, my name is Suzie, and I lead a small research group at the University of Oxford, and we mostly work on photon accelerators, and I'll introduce at the end of the talk one of my research projects. You can see here some of the people that I work with. This is in my lab, by the way. I have the privilege of having built a lab from nothing. It was an office before I turned it into a lab. So this is me. This is two of my colleagues from a local big national laboratory called the Rutherford Laboratory, David and Shinji. And on the right is my student, Lucy, who's in her third year of PhD. So she's my only PhD student at the moment, and that's another student. So I'm an accelerator physicist. That means I work on designing and understanding the beams and machines of particle accelerators. So I'm not quite a particle physicist, and I'm not a medical physicist. So just to clarify where I lie. I do science communication as well as research, so I do a bit of TV presenting, and I did a TED talk last year, so you can watch that if you like. And in my spare time, I really enjoy good food, so I'm enjoying visiting Indonesia for my first time being here. And I also like running, so just to give you an idea of why. I haven't been running here, it's too hot. On the treadmill right now. So I was born in Australia in a little tiny town called Mildura, which is on the edge of the desert. So I don't come from a big city, but I moved to one when I was quite young. And I did my degree in physics at the University of Melbourne in Australia. And then I moved, like London, I moved to Oxford to do my PhD, or DPhil as we call it, in 2007, where I was working on new types of accelerators for proton therapy. And I haven't put much in about this, but you can ask me after if you like. After that, I had my own research fellowship, which let me do research on high-intensity proton accelerators. So I'll talk a little bit more about those at the end of this talk. And from 2017, I have a new fellowship, which allows me to grow my research as well. Now things keep changing, so from this year, from March, I will actually split my time between Oxford and Melbourne University, where I will become a senior lecturer, and I'm going to be starting a new research group there, focusing more on medical applications of accelerators. And there will be master's and PhD positions available, so I will let you know that in case you might be interested in joining my group in the future. So when people think of Oxford, where we both work, they usually think of these beautiful old buildings, which they really are lovely. But my building looks like this. Not so nice. Just to give you an idea of where I sit every day. It's never that sunny in Oxford, by the way. It rains a lot. Right. So to test your knowledge, how many particle accelerators do you think there are in the whole world? Not including televisions, just in case anyone wants to guess that. So I'll let you think for 1 second. So who thinks A, 1 to 100? Who thinks B, 100 to 1,000? C, 1,000 to 10,000? D, 10,000 to 50,000? Okay. E, more than 50,000? Everyone else says, I don't know. Yeah, quite a few people say, I don't know. So the answer is D. It's between about 10 and 50,000. And those of you studying medical physics will probably realize that there's more than 10,000 just medical accelerators in the world. So where are they? Well, about half of them, there's about 35,000 is the correct estimate of how many accelerators there are. And about half of them are used in medical applications, mostly radiotherapy, some radioisotope production, which I'll show a picture of later, and very few with proton therapy and targeted therapy. Most of the other 50% are used in industry. So I'll show you some of the applications of those in a minute as well. Or I should say, less than 1% are the big machines used for research and particle physics. And usually when I say particle accelerators, that's what people think of as the very big ones. But by numbers, the small ones are much, much more common. So where did this all come from? Why do we have particle accelerators in the first place? Well, the story starts back in the early 1900s. And of course, if you're studying physics, you will remember this, that in the early 1900s, we didn't really know what the atom looked like. So the English physicist J.J. Thomson, the one who discovered the electron, he thought that it looked like what we call a plum pudding. So it's a pudding with like raisins, like fruit in it. So he thought that this was sort of a positively charged sphere with some negatively charged parts within it. But of course, Ernest Rutherford and his colleagues did the experiments using alpha particles onto a very thin gold foil and found that some of the alpha particles bounced straight back towards them. And that was evidence for the atom being more like what we understand today, which is a big cloud of electrons around the outside and a very small, very dense nucleus in the middle. So this is before we have anything like particle accelerators. Now the decade in which accelerators were really developed, probably for the first time, is the 1920s. And my students always think it's really funny when I show these pictures of what life was like in the UK in the 1920s. So cars were sort of a thing. They were not very sophisticated. They were beautiful, not very sophisticated. But for the first time, there were lots of electrical appliances that people started to use. So it was in the 1920s, in places like the UK and the US, that most homes got electricity for the first time. So they started using electric vacuum cleaners, radio became a thing, and also electric toasters became a thing. And my students loved the fact that in houses in England in the 1920s, electric toasters were really fashionable. So instead of just having one in the kitchen to make toast, they had them in the bedroom and in the bathroom because it was a sign, of your wealth that you had electric toasters. Very strange. But anyway, the point is, most of the population were just familiar with electricity. So the fact that there were scientists out there using the principles of electricity and magnetism to investigate the fundamental nature of matter is quite amazing, given what the daily life was like. So in 1927, Ernest Rutherford, who I've mentioned already, he's from New Zealand, by the way, because he wasn't British originally, made this speech at the Royal Society, who is a big organisation in London who now fund my research. And he said it has been his ambition to have available for study a supply of atoms and electrons which have an energy far greater than the energy from the alpha and beta sources that they've been working with before. So this is commonly held as the first time that someone has stood up and said, we need particle accelerators. We need a machine that can take atoms and electrons and make them faster or give them more energy than they have naturally from radioactive decay. And as a result, a number of different types of accelerators were developed, and some of the first ones look very different from the ones that we have today. So some of the first ones were what we call electrostatic accelerators. And one of those types is called a Popoff-Walton accelerator. And it turns out if you build a circuit that looks like this, which is a voltage multiplier circuit, and you stack those circuits on top of each other, or
multiplied many, many times, you can take a fairly low AC voltage and convert it to a very high DC voltage. And as a result, they were able to get up to things like 1.2 megavolts of acceleration using some of these devices. And this was actually a picture over here from Cambridge University in the UK of one of these very fancy looking accelerators which they actually used to split the atom for the first time. Something interesting in this picture is Walton, the guy who's taking the measurement, is sitting in this box underneath the experiment. So as they did the experiment with these particles from the accelerator, they would hit a phosphor screen in this box, which would light up, but they had no electronic way of detecting that light. So he would sit there and he would wait until he saw the light and then record the result. So not very safe. Not very safe at all. But that's how it used to be done. A bit more sophisticated. The other type of early electrostatic accelerator was a Van de Graaff accelerator. Have you played with the Van de Graaff dome that makes your hair stand on it? Seen that? Yeah. So same principle. It's an electrostatic accelerator where charge is built up on the outside of a dome here. And these got up to I think 40 megavolts was the highest energy Van de Graaff accelerator that I'm aware of. But the big challenge with these types of very high voltage accelerators is they break down a lot, they spark a lot. It's very difficult to maintain a very, very high voltage. But a lot of early work in nuclear physics especially was done with that type of machine. So to reach that sort of 40 megavolt level, they even did things like they would send the particles down and to be accelerated once with one charge, and then they would strip the charge from the ion and send it back through the other way to be re-accelerated. So they would use the voltage more than once, but usually twice with the unit. And Robert Van de Graaff was actually a student in Oxford at some point in his career. So those are the very early accelerators, but of course we've come a long, long way from then. So this plot shows you over the time of year of commissioning from, this is 1930 down here, up to sort of 1990 on the right. Shows you technically the center of mass energy of the machine, but it's sort of a measure of machine energy. So it shows you how different generations of particle accelerators and new inventions in the field of accelerators led scientists to be able to get higher and higher and higher energies. And the reason they did that is because the higher energy we have, usually the sort of smaller thing, that you can investigate. But this has always been the drive in particle physics, is to get to higher and higher energy. Until at the moment we have now this huge machine, the Large Hadron Collider, which is near Geneva at CERN, and I've had the privilege of visiting this machine a number of times. It's really, really mind-blowing. So it is 27 kilometers long, the ring. It's 100 meters underground. And all the magnets in this machine, these blue things of magnets, are kept at 1.9 degrees Kelvin. So liquid helium, low liquid helium temperature. So it's also the biggest refrigerator in the world. And it's designed to take two beams of protons and accelerate them to, this is accurate, 99.999999% of the speed of light, which is 7 tera electron volts. So many factors higher than a medical machine. In opposite directions, and then squeeze the beam down to less than the width of a hair and collide them head on. It's pretty tough, right? It's pretty impressive. And so the question really is why did we build it? Why did we build it? And
And, and the answer really is to try and understand at the most fundamental level the building blocks of everything around us, right? So we know, from the ancient Greeks we have the idea of atoms. Through nuclear physics we understand how, how atoms consist of different nucleons, neutrons, protons, and so forth. But inside all of those particles are quarks. And then there are also particles that exist in nature that play no role at all in everyday matter. So trying to understand how the picture of the universe is built up from its smallest parts is really the reason we built this machine. But particularly to find one particular particle which was the missing piece of this puzzle, which is the Higgs boson over the right there. Can you tell me if you've heard of the Higgs boson before? Some people? Some people never heard of? Maybe in the news or something. Yeah. Okay. So all of matter, well, all of the matter that we deal with every day consists of the two quarks, the up and down quark. So they make up the protons and neutrons. So it's two ups and a down and a proton, and two downs and an up and a neutron. I'm pretty sure I got that right. And electrons, so that's atoms right there. Neutrinos are involved in beta decay. But then there's two extra generations of this matter that we've discovered over time. And each generation is heavier than the last. We think there really are only three, though, we believe that. We have evidence for it. The photon, of course, is involved in light and electromagnetic interactions. The gluon is what binds the quarks together into things like protons and neutrons. And the Z boson and W boson are involved in weak nuclear decay. But the Higgs boson in the equations is required to make everything else make sense. Because in the equations, there's a term M for each of these particles, which indicates its mass. And if the Higgs boson didn't exist, all the masses would be equal to 0. So the theory says that there should be this particle because we know the other particles have mass. But of course, for many, many years, they didn't have any evidence of it. But now we do. We do have evidence that the Higgs boson is real. We don't know that much about it yet, but that's why we're still continuing these experiments. So over time, we've learned all of this successively by building larger and larger accelerators and going to higher and higher energies. So all of these different particles were discovered over time as the energy of the beam of the machine went up. Because as you annihilate particles together, the more energy you have in that collision means the heavier mass particles you can create. And as we go up in mass, that means our machines have to get bigger and bigger. But we are almost at a point where we're starting to question, okay, well, what comes next? But there are many open questions we don't know the answer to. This still only explains about 5% of the mass of the whole universe, all of this stuff. So there's a lot of open questions. But along the way, of course, we've developed many, many new technologies. This is a picture of an event display from the Atlas detector, one of the Large Hadron Collider experiments, showing some of the particles, some of the protons coming in, colliding, and then producing all kinds of debris. And it's from these kinds of images that they're able to reconstruct what happens actually at the collision point. But interestingly, a lot of the detectors, a lot of the algorithms, a lot of the computing technology that goes into this kind of experiment then is able to be picked up and used elsewhere in society. So it turns out to be quite valuable. So I want to quickly go through how accelerators work. And they all work in a very similar way, actually. And really, this is a diagram of a cathode ray tube television, non television. It has all the ingredients of a particle accelerator. So we have some form of cathode or some source of particles here. In this one, it's spit out electrons. You have some accelerating structure, so some voltage usually that gives energy as the charged particles pass through it. You then have some control system with usually magnets that
in this case a coil, which controls the direction of the particles, and also some focusing as well. A lot of people forget that you actually have to focus within the particles as well as bending it around. And then at the end, the particle beam does something. So it either collides or it hits a target to generate X-ray or so forth. So that's all the ingredients that you need. So for something like the Large Hadron Collider, to get the particles for that, they actually use something called an ion source, which starts with a bundle of hydrogen gas. And if you take hydrogen gas and form a plasma out of it by applying a very high voltage, you can separate the protons from the electrons and rip them apart and end up with the protons coming out into your machine. So but you don't require much hydrogen to get billions of protons, so it's only a small quantity of hydrogen required. And the next step then is to accelerate the particles. And we do that in a more sophisticated way now than we used to. So in a linear accelerator, there's two different types of linear accelerators. And the early ones were called drift tube linear accelerators. And they work like this. So you have a charged particle that's coming in, and then you have some kind of drift tube inside which there's no electric field. Because if you remember, inside a conducting surface, there's an electric field on the inside. So the particle only experiences the electric field when it's between the tubes. Now, when it goes between the tubes, it gets a kick from the electric field it experiences, and then you swap the polarity of the field. So, but it doesn't see it. But that means that when it comes to the next gap, it gets accelerated again. And swap again, the next gap it gets accelerated again. But you have to time it correctly. So as your particle gains energy, it gets faster. And that means that the drift tubes have to get longer with the velocity of the particles in order for the frequency, if you always apply the same frequency of electromagnetic field to that kind of structure. So this was introduced by a guy called Kuliah Umum, but this isn't quite, this structure is still used, especially in some proton accelerators, but it's not quite the same as the one that's used in, okay, you've got to have that. Yeah, so this is just showing you how to change the polarity of the particles accelerated in the drifts and gain energy. So that's not quite the same as the one used in a medical accelerator, which looks, so that's the one I just showed you. The one in a medical accelerator looks a little bit more like that one on the right, where instead of having drift tubes, instead you have electromagnetic fields which have usually standing waves inside the structure. So you get an electric field that successively points forwards and backwards inside each section of the cavity. And again, you have to time the passing of the particles through correctly so that it's always accelerating and not decelerating the particles. But there are many different ways you can arrange this structure. So these show some of the layouts of some of the different types of cavities, as we call them, where the beam pipe goes through here. And if you imagine, this is 1/4. So if you flip it out, flip each of these out along this axis, and then rotate it around the central axis, that gives you the three-dimensional picture. A bit of mental work. So there are many different ways that you can organise this, and for different particles, different energies, different applications, we do it in many different ways. This structure over here, you would use if you had a superconducting RF cavity rather than a normal. But in the end, you get something like this, where you can pump in the electromagnetic fields, and they set up a very nice standing wave that's very efficient. And as you send your particles through at the correct time, you always gain energy instead of losing it. So that allows you to gain more energy than you'd be able to with a static high voltage, because you're able to use the same electromagnetic field again and again. Just to give you an idea, this is what the Large Hadron Collider cavities look like. So, a medical reactor, this big. In the Large Hadron Collider, this structure is about as tall as me, and that's because the frequency required is much lower, so it's 400 megahertz, the frequency of these cavities. And the lower the frequency, the bigger the visible cavity. So that's because protons are a lot slower than an electron with negative emission. And that's also a superconducting machine. So far we've got a particle source and we've been able to accelerate the particles. So if you have an accelerator like that, it's either electrostatic or linear, and there are many, many applications of a machine like that we now use. There's mostly a list of them. So you guys are familiar already, I think, with X-ray Linux. So that's just a small linear accelerator. This is a 3 gigahertz frequency. And the beam is then bent round onto a target which generates X-rays, and the rest you know more about than I do. So the reason I'm visiting here and visiting your professor is because we're actually looking at the moment at why these machines have downtime and failure, particularly in some areas where there's lots of power cuts and things like that. And as a very large international collaboration, we're looking to change the technology to make it better suited to those environments. So it's very, so I'm learning a lot about these at the moment. You could probably teach me. One of the other big applications that people forget exists is if you have a computer or a smartphone, the chips inside those devices are made using ion implantation. And you can't do that using chemistry. You actually have to use a little, usually electrostatic particle accelerator to implant ions one by one into the chip. That's quite an important application. This application alone is billions of dollars market worldwide. Another one that, well, I experience a little bit because I travel quite a lot is things like cargo scanning. So, you know, if you go to an airport, you have to have your bag scanned by an X-ray machine. But if you have a much bigger structure, like a truck, then X-rays aren't going to get all the way through, usually. So they have to use either much higher energy gamma rays, something like that, or they can even use neutrons. But to generate the beams of gamma rays or neutrons, they need, again, a small accelerator. And so they actually they mount an accelerator on a small accelerator in a sort of arm-like structure that the truck then drives through, and they create an image of what's inside. I think this is an X-ray based one, and that these X-rays are far more penetrating than say a cobalt 60 source. One of the interesting problems with this, of course, is if people try and hide in trucks, because international rules on radiation say that you're not allowed to accidentally irradiate someone. So you can imagine trying to get good resolution while reducing the dose so that you can't harm someone. It's quite an interesting problem, actually. Right. So another very common one is electron beam processing, which is not very glamorous, but it's very, very useful. And one of the key things that they do with electron beam processing is a process called polymer cross-linking. Sorry, you can't read that very well. Where literally the chains of polymers using electrons means that you'll disrupt and form more and more bonds between the polymers, which changes the mechanical properties of things like plastics. So in the US alone, something like $50 billion worth of products get treated with electron beam processing. So it's everything from wire, the tubing that goes around the cables and wires, to curing ink on printed material, making shrink film, automatic shrinking films, making car tires strong, and all kinds of other things. This turkey is there because the shrink wrap around turkeys in the US is treated with electrons so that it shrinks properly and stays strong. So that means that without without chemical processing of these materials, you can make them strong against things like heat. You can increase the tensile strength, and you can give them special heat shrinking properties, which is quite neat. So this usually uses quite high intensity but low energy, like 10 MeV electron beam. More controversial application is the irradiation of food, which many people have heard of. But this process, with a much lower radiation dose than the previous page, allows you to change some of the properties of food sometimes. So with a very low dose, you can delay how long it takes for a banana to ripen, which means that it has a longer shelf life, which economically is a good thing. So they tend to package food into some boxes and send them through a conveyor belt, and they then some electron beams scanned across them to deliver the radiation. So other areas where this is used is often with herbs and spices. Because if you grow herbs and spices and then dry them on the side of the road, there might be some bacteria or some pathogen or something in there. So that allows you to get rid of anything that might be harmful to health when you package up the herbs and spices and send them on. So there's loads and loads of other ones. I have some endless list of applications in industry. But some of the ones that are quite interesting at the moment is hardening the surface of artificial joints that are put in people's bodies to affect how the body reacts to the surface. Because some bodies will reject an artificial joint, whereas if you study how the surface needs to look, the body is more likely to accept it, and it's a much more successful operation. They can remove things like nitrous oxide and sulfur oxide from flue gases from usually power plants. Scratch-resistant furniture. They can also treat wastewater to reduce the levels of chemicals put back into the environment after factories use the water. South Korea taking that one up quite actively. And another one which I find quite interesting is the gemstone industry uses electron accelerators a lot. I didn't know this when I learned it, but there's a gemstone called topaz, the bright blue, sparkly one. But often it comes out of the ground looking sort of pink, like boring and pink. And if you irradiate it with electrons, it can change the crystal structure in the material and change it back to the bright blue that we like. So for very little money, you can make a much more valuable gemstone. And they also do this with diamonds to change the color of diamonds. It's really interesting industry. Okay, so that's sort of small, usually small accelerators, and what we use those for. But a lot of my background has been on larger accelerators and particularly circular accelerators. So I want to introduce you to the two main types of circular accelerators. And the first one is the cyclotron. So have you heard of a cyclotron before? Most people? Yeah. Okay. So this was invented by Ernest Lawrence when he realized, he wanted to take a voltage like a RF cavity, but he wanted to be able to use it again and again and again. So he wanted to be able to bend the particles around using a magnet and send it back through the acceleration gap again, because it would be more efficient. And he realized that he could write down the centrifugal force, so mv squared over r, or I've got a rho in this case, the bending radius, and he could equate that to the Lorentz force, so the force the particle experiences in a magnetic field. And he realized that if you do that, you can cancel out the radius factor, and what it will leave is that the frequency of the circulation of the particles in a constant magnetic field would be constant. So that was very important to him, because it meant that as the particles were accelerated, he could the frequency of the accelerating field constant, the RF field, but the particles will continuously be accelerated by it. As long as constant charge and mass, then the RF frequency can be constant. There is a problem with that statement though, and I wonder if anyone's thought of it. What's the problem?
The orbit radius is proportional to speed p. If we are constrain the maximum speed of the particle.
Yeah, so, but you can let the particle increase in radius, that's fine. That's what he did, in fact. Let me show you actually. So he started the particle at a small radius, and as it accelerates, it spirals upwards, but that's fine. The key thing for him was that he wanted that to always be a constant frequency, so it would always take the same time to come around, regardless of the size of the orbit. Any other problems you can think of? Mohammed's got it, but I expected he might. What happens when the particle gets really fast? Does the time of... Well, that's going even further, but does the time always stay the same when the particle gets really fast? Like when you approach the speed of light? No, okay, so when you include relativity in this, so this doesn't include relativity, right? So if you include relativity, it breaks down. So once you get close to the speed of light, the revolution time is no longer the same, because you're no longer in. On each of these orbits, this is a slower orbit, this is a faster orbit, so that the revolution time is the same. But once you reach relativistic speed, the speed is always the same, which means that as you have a bigger circle, the revolution frequency gets slower and slower, and you're no longer accelerating anymore. So that's why the energy limit of a cyclotron is limited. You can't keep going up. The other problem is you end up with a very, very big magnet to keep circulating the particles around. But the very first cyclotrons were very, very small. This literally fits in the palm of your hand. And they built it in the lab, very quickly to test the concept. And the concept worked. And as long as you're using, say, protons, which are heavier, you don't reach relativistic speeds so quickly. So you can still use protons up to what I would say medium energy. The other, ignore this comment, it's from another lecture. The other thing you need to be able to do in a cyclotron, as well as bend the particles around it, is provide them with some focusing. And also at high energy, so there is a natural form of focusing from this machine, but at high energy you lose the focusing ability. And so they actually made cyclotrons into what are called separated septive cyclotrons, so that the magnetic field varied as the particles went around, and that actually managed to introduce additional focusing to keep the particle being stable as it was accelerated. So one of the really useful things with cyclotrons is that you can have all of the beam in it all at the same time. So you can inject the beam here and just fill the whole cyclotron, so you have a constant beam coming out the other end. And that means that the average beam current can be very, very high in a cyclotron, which is very useful. And the place that, especially in your field, is most useful in is radioisotope reduction. So here you use usually a cyclotron with a beam energy, either a low energy of something like 10 MeV or a higher energy of 70 to 100 MeV, and you smash those particles, usually protons or neutrons, into a target material, and from that create radioactive isotopes that you can use in diagnostic procedures like PET scans, which I think, on the medical physics course you will have heard of PET scans already. If you take that idea to its extreme, you can get high, sort of medium high energy and very high intensity beams of protons. And that's what they do on this machine, which is at the Kuliah Institute in Switzerland. And it was, for quite a while, the highest power machine, the highest power proton accelerator in the world, where power is the multiplication of the beam energy with the beam intensity number of particles. So cyclotrons, even though they're pretty old now, are still used for both cutting edge research and in lots of applications. The other place that cyclotrons are really common is actually in a new type of cancer treatment using accelerators, which is proton therapy or charged particle therapy. So some of you will have seen this before. So if we draw a plot of the depth in tissue in the body and the dose delivered for a single 6 megavolt proton beam, you get a distribution that looks like this. But if you use protons instead, or charged particles, they have a different interaction in the material, and so they come in with, for a small beam, with a lower dose on the way in, and then they slow down, and as they slow down, they increase the dose until it peaks right at the end of the range, and then it stops. So there's no dose after that. Now that, in reality, that is a very, 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 very narrow depth. And so in real treatment, they tend to spread out this so-called Bragg peak by just having a larger range of energy. So the starting energy determines where that peak is. And the idea with this is that you can have a greater radiation dose deep in the body, deep tumours, less dose to healthy surrounding tissue, and hopefully less damage to the organs surrounding it as well. So why is that different? Well, you have, instead of having photons, massless protons interacting in tissue, instead you now have a charged particle which is then interacting in a different way with the nuclei and the electrons in the material. And the equation that describes that is the beta-Bloch equation. And I'm sorry, there was some animation here and it's being lost in my slides, so just look at this one. So the dEdx, the energy loss per distance as you travel into the material, is inversely proportional to the square of the velocity. So that means that when the protons are traveling with a high speed, there's a small energy loss. At low speed, they have a high energy loss, and that's what gives you that characteristic Bragg peak that we saw on the previous slide. So I'm now going to show a very unfair comparison. So this is, if you were to take a single field, and of course you would never do that, right? But if you were to take a single field of photons versus a single field of protons, you can immediately see the difference that it makes by having a high dose at the end of range and the particle stopping. Now, of course, this is not a real treatment plan. This is never good. But for example, in a case where you need to irradiate all the way down the spine, so this child had a medulloblastoma which was removed from the base of the skull, and then they needed to irradiate down the spine. If you weren't careful, we don't do this, sorry, you can have a reasonable dose down the spine, but of course you would end up with additional dose in the rest of the body which you can help to deliver. But because in the proton case, the protons stop at the end of their range, you can use that in your contouring to deliver a higher dose along the spine, for example, and no dose at all in the rest of the body. So that's sort of the headline reason as to why proton and other charged particle therapy is a valuable tool in some cases. So there are many, many developments in that field now. So from techniques like spot scanning, being able to sort of paint the area you want to paint. Proton radiography, so actually making images using the protons themselves. Treatment gantries, so being able to rotate the beam all the way around the patient. Because the beams are heavier and much higher energy, the equipment is much, much larger. Right. And so I put FFA accelerators on there. This means fixed field accelerators. This is what I did my PhD thesis on. Answer questions about it later. And there are newer ideas in the accelerator field as well about very novel structures using things like dielectrics or even plasmas to accelerate beams to the right energies to shrink down and improve the technology. These are not working. They're not going to be working for quite a while. This one is closer, but still hasn't been built yet for that. Right. So I just wanted to sort of say there that there's many developments that come from people who work on, say, particle physics technologies that can make their way back into medical technologies. But what these people often need is good collaboration and communication with medical physicists and other people in the field to know where the problems are and what's needed in the technology. So that's why it's always good to talk to people like this. Right. So just to sort of, I'm winding up in a little bit, but I want to show you some of the principles of machines that go to even higher energies. And actually, most of the particle physics machines that we have are machines called synchrotrons, so a different principle again. And synchrotrons were invented in the 1940s, and the original idea was if you want to go to higher and higher energy, you can't have one enormous magnet like in a cyclotron. So instead what they wanted to do was make a ring of magnets and keep the beam always on the same trajectory, always on the same path bringing those magnets. So that was a different way of thinking about how we accelerate particles. And this guy, Marcus Oliphant, I'm very proud because he's Australian, he came up with the idea in the first place, and this just describes that what he wanted to do was vary the magnetic field to always constrain the particles on one single orbit. It's quite a difficult thing to do. So this is how we end up now with machines that look more like this. This is one of the machines that I work on, which is called the ISIS neutron and muon source, which is about 15 miles south of Oxford. And so what we get instead is separated functions. So we get magnets like this, which bend the beam, dipole magnets. We get quadrupole magnets, which do focusing and defocusing. And then we get the accelerating cavities as well, the RF cavities, all separated. And the way this machine works is you have, over time, you have the magnets power supplies ramping up and down in time, usually following a sinusoidal path. So the magnets are being powered and depowered, as it were. And you inject the particles at the low magnetic field point. You accelerate them, and you have to ramp the field up precisely as you accelerate them. And then when they reach the top energy in the top magnetic field, you extract them again, and then the magnets come back down, ready for the next cycle. So because you have to synchronize the magnets and synchronize the acceleration and the acceleration frequency, which also increases, that's why it's called a synchrotron, because you have to synchronize everything there. So this just shows you, you can control, for example, the radius of bend of the particle, and you have to increase the magnetic field because the higher the energy, the higher field you need to keep going on the same path. The other important function in the synchrotron is being able to focus the beam, and for that we use quadrupole magnets, where it's like having a north-south structure. But along the central line here, the field that you experience is actually linear, so it's a stronger magnetic field towards the outside of the magnet, zero field in the middle, and stronger in the other direction towards the other side. And if you think about that for a little while with the Lorentz force, you should be able to convince yourself that if you have a charged particle beam in there, this magnet will focus in one direction, but it will actually defocus in the other direction. So there is a solution to that, which is to place focusing and defocusing magnets after each other, so that overall the beam gets sort of squeezed and stretched. Gets squeezed and stretched in each direction as it goes from magnet to magnet to magnet. So if you were to look down the beam pipe of a particle accelerator, the beam doesn't just look like a single point. It looks like this. It's actually sort of stretching and squeezing as you go along. There is a equivalent to this. So this is a demonstration that I have in the UK to describe how sometimes with some setups it's a stable, this is a stable thing, and sometimes it's unstable. So the job of people like me, the first job we do, is to figure out the strength of those magnets and the distance between them in order to make sure that that beam is stable. Because if you imagine that this is a mechanical equivalent to this, believe it or not. You can imagine that if I spun that too quickly, or if the sides of the saddle were too high, the ball in the middle would actually just go flying off. So there's only certain conditions under which these beams in these accelerators are stable. And it's the job of people like me to try and design them so that they are stable. And if you do that correctly, you're able to contain many, many particles in a machine like this. So many, in fact, that they become a little bit dangerous to themselves. So if you have a very high intensity beam, now the particles start interacting with each other through a process called space charge. Because they're all charged, right? So they're all actually going to repel against one another. And in a medical machine, that happens right down at the very low energy end. But in a proton machine, it can happen all the way up to high energy. It means that you've got to control your beam very, very well. So if you lose a high power proton beam and it hits a piece of metal, depending on how many particles there are, it can do a lot of damage. It can melt the beam pipe of the machine. These beams actually have the ability to destroy the accelerator. So they can be very, very dangerous. So the job that I've been doing for a number of years, along with colleagues, is trying to understand in detail the dynamics of these beams. Because once you get to high intensity and everything is interacting, it's like a very complex galaxy where every particle is interacting with every other one. And solving that is a very, very difficult challenge. But one of the applications that you have once you have this very high intensity proton beam is to be able to generate neutrons very effectively. So this is what they actually do at this accelerator south of Oxford, called the ISIS neutron muon source. So they have a linear accelerator over here that injects into a 800 MeV synchrotron. So it's not very big compared to the LHC. And that happens 50 times a second, that the beam gets extracted from that machine at 800 MeV, and it's sent down one of two different beam lines where it hits a heavy metal target, and then that heavy metal target gets excited by this high energy proton and starts spitting out neutrons in all different directions. And then those neutrons are used to do all kinds of interesting science. And neutrons are very useful for that because unlike X-rays, where X-rays see heavy metals, for example, X-rays see heavy elements more differentially. Neutrons go straight through the heavy ones, but they interact most strongly with light elements like water. So this is, if you X-ray, this is a coffee maker, by the way. If you X-rayed a coffee maker, you would just see the metal on the outside. But if you do it with neutrons, it's a different picture completely. The metal is transparent, but the plastic of the handle is very dark, and the coffee itself, which contains lots of water, is very dark because the neutrons interact with the nucleus of the light elements in particular. And this allows them to do lots of very interesting studies there. One of the ones that they did was bringing in a piece of the wing and the body of the Airbus A380 aircraft, so the really big one. and they wanted to test the stresses and strains in the join of the wing. And to do that, they sent neutrons through the join while they were stressing it and straining it. And the neutrons were able to map out the stresses and strains in the join without destroying it. That's quite useful. If you were to be able to generate even more neutrons, one of the things they would like to do in the future is to get rid of nuclear waste from nuclear reactors. And the way that they can do that is by having a high energy, high current proton accelerator, sending that into the core of a reactor that has a material called thorium instead of uranium in it. And inside here there would be a target which would produce neutrons, and you would mix in with the target the high-level nuclear waste that you need to get rid of, so it's the transuranics that we know. And if you do that and you generate the neutrons in there, the reactor can send all of this high-level nuclear waste through its decay cycle, so that instead of storing it for hundreds of thousands or millions of years, it reduces the lifetime to 500 to 2,000 years, which makes the waste much more easy to deal with, and means that we're not leaving future generations with a huge nuclear waste problem to deal with. So something like this is going to be necessary, even if we would stop building nuclear power plants now, if we wanted to, because we already have so much waste that needs storing for millions of years, that in a way we need a solution. We need a solution anyway. Now, if you do this in a thorium reactor, you can actually make power out of that as well. You can actually generate electricity with the reactor, send some of it back to the accelerator, and some of it back to the grid. Now, this is not being done. Right? So, but the challenge here is you need an accelerator which is 10 times more powerful than the ones we build at the moment, and about 1,000 times more reliable. So actually these guys are learning from things like the medical accelerator community how to make accelerators more reliable. Because if this thing switches off many times a second, or for some time, it affects the thermal properties of the reactor side, which isn't good. So that's a really interesting bit of research happening. But to make things like that happen, we have to understand how the things really behave in intricate detail. So I just wanted to finish by showing you one of my experiments that I'm working on. So this is an experiment that's not an accelerator, it's actually an ion trap. And inside a vacuum vessel, I have a structure that has four cylindrical rods, and they form the same structure using electrical fields as an accelerator has in magnetic fields. And so what I can do with that is set up is to stably trap particles inside there, so it has an oscillating electric quadrupole field. And we can stably trap argon ions inside there and then manipulate them as if they were in an accelerator. So you might remember this picture from before. So inside this trap, I have argon ions which are doing the same thing as this. But the nice thing is I can do whatever I want. I can manipulate it, I can model any accelerator, and I can have as many particles as I like, very, very high intensity. And it's not dangerous because there's no energy, so there's no radiation produced. So this is what my PhD student is working on. And this is the same thing but using pollen particles. So you can't see in real time, unfortunately, what happens in here. But this is what we're trying to do. And so using this technique, I'm trying to model future accelerators that we haven't built yet with new concepts for how to build the accelerator, so that we can see whether or not they will be stable and whether they will work at high intensity without spending literally billions of dollars to build the real thing first. So I just want to finish by saying that hopefully you have an idea of how over time, as we've developed accelerators for particle physics, slowly over the years they then get taken up, the same technology gets used for all kinds of wonderful applications that can both do things like treat cancer, but also even help us in industry, create our mobile phones and so forth. So hopefully that's inspired you a little bit to think about what we might be able to do one day with the machines that we're still using in physics lab. So, thank you.
Thank you very much, Suzie. Only one also question. Any question from the room? Yes.
Okay, thank you very much for your lecture. Actually, this is very hard one and difficult one, and I cannot process it all. But my question is, well, the first one is the thing that you have said that the accelerator have a benefit that can strengthen the joint.
Yep.
Yep. And I want to know what is the behind the processing for that? Maybe because the particle make the structure change the structure of maybe the something to do with the structure of the joint, artificial joint, make it more more rigid one. And then is that clear what I say?
Do you mean the artificial joint for the body?
Yeah.
Yeah.
So I mean that what is the effect and what's behind the process?
Right.
Why the joint become more applicable for the human after it get irradiations?
Okay, thank you. Very good question. So it's less about the strength of the joint, and it's more about the surface property. So a real bone, the surface of a real bone isn't perfectly smooth, right? It has some structure on the surface, and the body knows that, right? Like your immune system, whatever other aspects of your body are aware of that. So what this process does is it changes the structure of the surface to be more similar to the real original joint. Yeah.
Okay.
That's my understanding. I only have a basic understanding of it.
Yeah. Thank you very much. That's very clear for me. And what about the you have said that about the application of charged particle, and now I have read about the neutron one that they should want to the using the neutron particle to use. Maybe that I have said it when the time of this afternoon lecture is about the boron neutron capture theory therapy that they use a collimated beam that consists of neutron, and after that they shoot to the part of the body that has boron on it, and finally the boron and neutron will react, and they will resulting in production of alpha particle and energy. And when I see the challenge is using the NCT or boron neutron capture therapy is very difficult, and I mean that we need an accelerator, and not every country have that. So I mean that what's the difficulties to processing this neutron?
So the difficulty with the real basic difficulty is you can't accelerate neutrons. So you have to start with, say, protons or something else, and then use that to generate neutrons. But the nuclear process to generate the neutrons requires some threshold energy, right? So you have to have an accelerator with sufficient energy to generate the neutrons in the first place that you can then use. I don't remember what the energy is actually. Do you remember what the beam energy is to produce the neutrons? It depends on the reaction that you're using. But there's always some threshold, and usually it depends on which nuclear reaction you're using to produce it. But I think I don't know with most BNCT machines which species they use to generate the neutrons in the first place. But it's but the other thing is, I guess you need a lot of neutrons. So that again means you need a high intensity accelerator to then create more neutrons. And the high intensity is at low energy, particularly, is very challenging.
Okay, so maybe with the energy, I don't know what from what I have read is I don't know how much they use the dose for the neutron, but I just only know that the final energy that have result that is about 0.25 meter-electron-volt. And then, but also it means that we cannot accelerate the neutron.
No, because you need an electric charge to be able to accelerate.
Then what about, I don't know this, maybe you can explain to us, but the rapid and slow neutron?
What about the what, sorry? Rapid and slow neutron?
Fast and slow neutron, because when I read some people that say that because when the neutron shoot to the particle of our body, that they consist of two neutron, and that is fast neutron and slow neutron. And what we need is the slow neutron to react with the boron. And the fast one is finally it just disappear because of our composition in our body, like hydrogen and etc. So what about that fast and slow?
Sure, so I'm not so familiar with it, but usually in any neutron production process, you usually generate them all at fast or high energy, and then moderate them down to make them slow. So usually there's some process which creates the higher energy, and then some of them will lose energy. So there are some very obscure processes involving the magnetic moment of the neutron that can give them tiny bits of energy. But as far as I'm aware, if you want to make them faster using electromagnetism, they have to be produced from another high energy using a target. Yeah. I don't know if that answers your question. But thank you.
Okay, thank you very much. Because I think Firman and Suzie have another short meeting with the Unhas. So I think we close the session, and thank you very much for attending this course. And I think I hope some knowledge, either really physics from Suzie, that will be discharged, or knowledge from physics perspective. Okay, thank you very much, and